Hi everyone. In this presentation, I will present recent work on sequential clinical diagnosis using LLMs. And I will also share what I think are the current limitations and open problems in this direction. The key question is not only what is the diagnosis, but also which evidence should we acquire in what order and when should we stop. So this slide shows the overall map of this talk. Uh, with this data set, we can now study sequential diagnosis with richer clinical text. So the task is no longer just predicting a diagnosis from complete information. The model has to decide what evidence to acquire next, interpret it, and decide when to stop. In this map, LA-CDM is the first major work that trains an LLM agent in this setting. And LDTL and SIFT then try to improve how we supervise the diagnostic trajectory. And CART focuses on a slightly different topic, so in this talk, I will mainly use the remaining papers to explain how this new research direction is developing. So the main question of this presentation is what is a good trajectory? Each patient has a ground truth diagnosis label, which tells us what disease the patient has, but there's no label telling us the best diagnostic path. For example, we do not know whether the best path is A to B to C or A to C to B. So this creates a supervision gap. Recent papers try to fill this gap with different proxies. So these papers can be understood as different answers to the same question. How can we learn good diagnostic paths without path labels? So let me introduce the dataset first. So this dataset contains 2,400 patient cases, and each cases has one ground truth diagnosis label. And the labels correspond to four abdominal diseases. So the important part is the action space. The model can choose from 12 diagnostic actions, including 7 lab test groups, 4 testing report types, and finally, physical examination. So in this benchmark, the model typically starts with limited information and sequentially chooses which action to take next until it performs a diagnosis. So the first paper is LA-CDM, which explicitly trains an LLM agent for sequential clinical diagnosis. The key idea is to make the model repeat the clinical loop, form a hypothesis, request evidence, update confidence, and then perform a diagnosis. So they start from two limitations in previous work. First, many clinical reinforcement learning methods are designed for tabular data. They can work with lab values, but they do not naturally handle clinical notes or imaging reports, which are often textual and very important for a diagnosis. Second, secondly, many LLM-based clinical decision-making systems relying on just prompting or zero-shot reasoning. They use the medical knowledge already inside the LLM. So, but they do not explicitly train the model to select tests sequentially. So this figure shows the overall structure of LACDM. There are two agents. The hypothesis agent reads the currently available patient information and produces a likely diagnosis hypothesis with confidence score. The decision agent then uses the agent state and the hypothesis output to decide what to do next. It can request another test, or it can stop and make the final diagnosis. So this design is inspired by real differential diagnosis. Clinical clinicians usually do not gather information randomly. They form a hypothesis, test it, revise it, and repeat this process until they are confident enough. So LAW-CDM tries to make the LLM follow this clinical loop. So this they uses three training objectives. First, hypothesis generation is trained with supervised fine-tuning. At each state, the hypothesis agent is trained to generate the correct diagnosis. Second, confidence calibration is trained with reinforcement learning. The model should not only predict a diagnosis, but also express uncertainty appropriately. If it is 60% confident, that confidence should match the actual correctness rate. So finally, the decision agent is trained for efficient action selection. It receives reward for a correct final diagnosis and a penalty for test cost. In short, they explore different test selection paths and optimizes the trade-off between diagnosis accuracy and some test cost. I will not go deeply into the results because LAW-CDM is mainly the starting point of this problem setting. The main comparison is with React. React is a prompting-based agent framework where the LLM alternates between reasoning steps and actions, but it is not specifically trained for these clinical decision-making task. So compared with this React baseline, this research achieves higher diagnostic accuracy and lower average test cost. So the key takeaway is simple. Explicitly training an LLM for sequential clinical decision making can improve both performance and efficiency. So, and the second paper is LDTL. This paper focuses more directly on the missing trajectory supervision problem, how to train good diagnostic paths. So the motivation of LDTL is that terminal reward is too weak for learning trajectories. In a reward-based setting, the model may only receive feedback at the end of the path, after the final diagnosis. So even if the final answer is correct, mm, it is still unclear which actions in the trajectory were actually useful. This means the reward can optimize accuracy and cost, but it does not directly supervise the structure of the diagnostic path. So this they formulate the test selection process as latent diagnostic trajectory learning. Instead of relying only on final reward, it constructs action level signals from diagnostic improvement. Hmm. There are two main agents, the planning LLM agent and diagnostic LLM agent. The planning LLM agent selects the next diagnostic actions based on the current patient state. For example, it decides which test or examination should be requested next. After the new evidence is added, the diagnostic LLM agent evaluates the updated patient state, and it predicts the disease label and estimates confidence. The important thing is that the diagnostic LLM is also used to measure diagnostic improvement. If adding a certain action increases confidence in the correct diagnosis, that action receives stronger training signal. So LDTL does not require ground truth path labels. It uses the diagnosis LLM. Changes in confidence as indirect supervision for training the planning agent. So this slide is the most important part of this research. Ideally, we would evaluate full trajectories. For example, we could compare trajectories like ABC, ACB, BAC, and so on, and so on. Then we could assign higher probability to trajectories that lead to better diagnosis. But this is actually computationally expensive because they grow exponentially. So in practice, LDTL approximates the trajectory posterior using one-step information gain. It asks, if I add this action to the current state, how much does the probability of this correct diagnosis improve? So the method has two stages. First, the diagnosis LLM is trained to predict the correct disease and output confidence when full patient's information is available. This gives a model that can evaluate how useful a path is for diagnosis. Second, the diagnostics LLM is frozen and the planner is trained. At each step, candidate action are evaluated by how much they improve the diagnostic model's belief in the correct label. This creates an action posterior. Then the planner is trained to match the posterior using KO divergence, like teacher and student. The results suggest that latent trajectory supervision improves sequential diagnosis. Compared with random selection and the planner without latent path regularization, LDTL improves accuracy and macro F1. It also changes the termination distribution. So more cases terminate after one step, and fewer cases require three steps. This means the model learns to gather useful information earlier. For my, yeah, for my interpretation, LDTL is a meaningful step beyond simple terminal reward, and it tries to supervise the path itself. And the third paper is SIFT. SIFT defines clinical evidence for each patient with a score that represent how important each piece of evidence is for the diagnosis. Oh, so they start from two limitations. First, past research usually restricts the action space to a predefined test menu and the diagnosis space to a fixed label set. But real clinical diagnosis is more open-ended. Secondly, terminal reward does not capture evidence quality, the same as LDTL. A model can get a diagnosis right or wrong, but the reward does not explain whether it collected the right evidence. So SIFT addresses this by rewarding trajectories based on the amount of critical evidence they recover. So this figure shows the overall pipeline of SIFT, but the key idea is that SIFT assigns important scores to clinical evidence and uses them as a reward signals. I think this figure is kind of messy, so it is better to explain specifically on the next slides. So they first perform fact extraction. The full patient record is decomposed into atomic clinical facts. Each fact should represent one observation that cannot be divided anymore. Then each fact receives a critically score from 0 to 3. A score of 0 means irrelevant, a score of 1 means supportive but non-specific, and so on and so on. The scoring is done offline, so during a rollout, the model does not call the scorer repeatedly. It simply receives reward later based on how much critical evidence was discovered. So the key metric is critical recall. So CR measures how much of the total diagnostically important evidence was discovered by the trajectory. The numerator is the sum of criticality scores for discovered facts, and the denominator is the sum of criticality scores for all facts in this record. So the reward combines three parts since they are using reinforcement learning. First, if the final diagnosis is correct, the model gets a correctness award reward scaled by critical recall. Secondly, if even if the diagnosis is wrong, the model can receive partial credit for retrieving critical evidence. Third, there is a step penalty, so the model is discouraged from using too many steps. This kind of rewarding design teaches the model that diagnosis is not just about the final answer. It is also about gathering the right evidence. So the key result is simple. Evidence quality matters more than evidence quantity. They shows that the ratio of critical evidence is more strongly related to diagnostic success than simply collecting more information. So the takeaway is that a good trajectory should not gather many observations. It should gather the evidence that actually changes the diagnosis. So this slide summarizes the common structure. LDTL constructs a trajectory and evaluates whether the trajectory improves diagnostic confidence or accuracy. SIFT evaluates the trajectory by checking how much critical evidence was retrieved. Both are trajectory level approaches, and both improve over simple final answer supervision. But they share an implicit assumption that the value of each piece of evidence is relatively independent. So in other words, if a test is useful, it is useful by itself. If a fact is critical, it contributes positive value to the trajectory. However, in real diagnosis, the value of one test often depends on what other tests are observed. A test may be weak alone, but very informative when combined with another test. This is the limitation I wanted to highlight. So this slide explains the main limitation more clearly. In the first example, action A gives higher immediate utility than B, so a greedy method chooses A. But after adding the same second test C, the combination B plus C becomes better than A plus C. In the second example, A again looks better at the first step, but B enables a better later test D, and the final trajectory B plus D becomes better. The takeaway is that greedy selection that looks one step does not fail only because intermediate reward is missing. Even with intermediate rewards like SIFT, evaluating tests independently can still be wrong. The deeper issue is conditional dependence. The value of one test depends on which later tests it can be combined with. At this point, I'm considering two possible directions, but the experimental experiments are still ongoing, so in this video, I'll keep the explanation simple. So the first direction is a Bayesian network. The idea is to explicitly model conditional dependencies between tests so that the value of the test of one test can change depending on what evidence has already been observed. So the second direction is n-step look-ahead training. Instead of evaluating only on the next test, we evaluate short combinations of future tests and uses that as learning signals. Both directions are trying to address the same issue. Diagnostic evidence is not always independent, but I will leave the detailed discussion for future work after the experiments are more complete. So, today I briefly introduced how this research direction is developing and shared my current thoughts. The experiments are still ongoing, so I hope to discuss more concrete results and ideas in the future video. Thank you.